Good morning, everybody, and thank you for the opportunity to give me the to speak here about my research, Jérôme. Before I start, Jérôme has already indicated the title of my talk, so I'm going to start. I'm going to show you some data on carbon dioxide concentrations in the atmosphere as reconstructed from marine proxies. But I would also like to acknowledge my co-authors. Mark is here. But the one that I would really like to acknowledge is Greta Bartoli, who came to my lab 1.5 years ago, and she initiated some analyses on Pliocene samples. So I'm also going to show some really new data on the Pliocene. So what I'm going to show you is, first of all, give you a very, very short introduction of marine carbonate chemistry and the use of boron isotopes for reconstructing seawater pH. And then I'm going to show you two data sets where I used seawater pH to gain information about atmospheric carbon dioxide. And I'm going to show you data sets across the mid-Pleistocene transition over the past 2.1 million years, which was just published last month. And then the newest data on the northern hemisphere glaciation during the Pliocene. So when carbon dioxide dissolves in water, it reacts with the water to form carbonic acid, and then that carbonic acid dissociates to bicarbonate ion and carbonate ion and hydrogen ions. And that is the reason why there's so much more carbon stored in the ocean than there is in the atmosphere. The relative abundances of these species are a function of equilibrium reactions. And those equilibrium reactions also determine the seawater pH. So if we know the different components of the carbon system in the ocean, if we know the relative concentrations of carbon dioxide, bicarbonate ion, and carbonate ion, the sum of them, the alkalinity, the seawater pH, those are the 6 parameters that describe the ocean carbon system. And we know, in addition to that, temperature, salinity, and pressure, that we can calculate all the others. So we only need 2 parameters of the carbon system to calculate all the others. Now, to give you a very brief idea of what I'm going after, is during interglacial times, when the partial pressure of carbon dioxide in the atmosphere is high, the partial pressure of carbon dioxide in the ocean also tends to be high, particularly in the oligotrophic ocean. And when the partial pressure is high, the pH is going to decrease. So we have more acidic conditions like we see today in ocean acidification. During glacial periods, the partial pressure of CO2 in the atmosphere is lower, and therefore the partial pressure of carbon dioxide in the ocean is also lower, and the pH in the surface ocean increases. So this is what I'm really going after, and this is what I like to reconstruct. And what I'm using for that is the boron isotopic composition of marine carbonates. And without going into the thermodynamic background of this proxy, how that exactly works, these are empirical calibrations that show the boron isotopic composition of various different carbonates. These are 3 species of corals, planktic foraminifers, that's another species of planktic foraminifers, and inorganic carbonates as a function of seawater pH. And you can see how the isotopic composition of boron increases with seawater pH. So that is the proxy that I'm using, and I'm not going into any more detail here. So what I want to reconstruct are two periods. The mid-Pleistocene transition, which is the time between 1,200,000, so 1.2 million years and 800,000 years, when the dominant cycling of glacials changed from the dominant 40,000 year cycle to the 100,000 year cycle of the late of the Pleistocene glaciations. And the other time that I want to show you data about is the onset of northern hemisphere glaciation, which occurred sometime between 2.7 and 3 million years ago. So as you can see over here, this is northern hemisphere summer insolation. The insolation changes of the eccentricity cycle, which could possibly determine this 100,000 year cycle, were not large enough to really drive this change. And therefore, there have been some other explanations brought up that could possibly lead to these larger ice extent in the Pleistocene. And one of those hypotheses is that due to the uplift of the Tibetan Plateau, there was a long-term drawdown of carbon dioxide as a function of weathering. So when silica rocks weather, they use up carbon dioxide and produce a lot of alkalinity, and therefore there's a drawdown of carbon dioxide in the atmosphere. And so eventually it would have become cool enough to explain the larger ice extent in the Pleistocene. there was another hypothesis, and that is based on the observation that the land ice extent in the northern hemisphere 2.5 million years ago was about the same as the land ice extent, just the spatial extent of the ice, 80,000 years ago. And so the only explanation how you could build up more ice is by basically building up larger ice sheets, thicker ice sheets, and not wider ice sheets. And so the way how that was explained was that over millions of years there was a weathered soil layer that had built up on the continents, and due to the repeated advance and retreat of those of the glaciers, this soil layer was eventually removed. And only when the solid bedrock was exposed, these really large ice sheets could really build up. So these are just two hypotheses that have been put forward, and I'm going to test this one that looks at the long-term drawdown of atmospheric CO2. I'm going to show you data from two sediment cores today. The first one for the mid-Pleistocene transition is ODP 668b in the eastern equatorial Atlantic. When I want to reconstruct carbon dioxide, I have to go into oligotrophic ocean areas, because I need to know that the carbon dioxide concentration in the surface ocean is the same as the carbon dioxide concentration in the atmosphere. So I cannot go into upwelling areas, for instance, where the surface ocean carbon dioxide concentration may be higher than the surface ocean than the atmospheric concentrations. So these dashed areas over here, those are upwelling areas as they exist in the modern ocean, and ODP 668b is far enough away from that I should not expect an upwelling signal. The other core for the mid-Pleistocene, unfortunately this core doesn't go back more than I think 3 million years. So I could not use that one for the mid-Pliocene. And so we switched to this core, ODP 999a, which is also in an oligotrophic area. It's a very small source to the atmosphere today. It's not exactly in equilibrium with the atmosphere, but both of those cores are very well studied, and they're relatively shallow, as boron isotopes actually have a dissolution effect. So I have to go and look into sediment cores that are above the lysocline. Now these are data that just got published last month, and it's a pretty busy figure, but I'm going to walk you through it just to give you an idea of what kind of information I need to finally tease out the carbon dioxide concentration. So what you see over here on the top panel, these are this is the oxygen isotopic composition of the Lisecki and Ramos stack from benthic foraminifers over 2.1 million years. And on the next panel, you see the boron isotopic composition of foraminifers. You can already see that during glacial times, the boron isotopic composition is heavier than during interglacial times, so that already indicates higher pH. But in order to calculate the pH from boron isotopes, I need to know something about temperature and salinity so that I can calculate my pK values. So the temperature, the sea surface temperature, we measured as a function of the magnesium-calcium ratio in benthic foraminifers, which is indicated over here. Then this is the sea level record from Bintania et al. In 2005, which I use as a possibility to reconstruct salinity in the ocean. So I can calculate salinity as a relative concentration when sea level was lower. So when sea level was lower by 125 meters, then salinity was increased by 3%. And that's what I've done over here. So this is the salinity scale to the local conditions in the eastern equatorial Atlantic. And so now I have salinity and temperature, I have the pressure from the depth habitat of the foraminifers, and I can calculate the pH from my boron isotopes. You can already see that during the late Pleistocene, pH was about 0.15 to 0.2 pH units higher during glacial times in comparison to interglacial times. Over here is one alkalinity estimate. One of the scenarios that I've used, and this is my preferred scenario over here. I'm going to show you a little more about that in the next slide. So this is my second parameter on the carbon system that I need to calculate pCO2 from pH. And down here is now the final CO2 estimate. Over here, the dark line, those are the Epica and the Vostok CO2 data, and relative to that, the pCO2 values are reconstructed from the boron isotopes. I'm going to show that blown up in a minute. So first of all, to give you a better idea of what I did with the alkalinity over here. On the top panel, you see the oxygen isotopic composition of planktic foraminifers, which I used as an indication of which ones are the glacial and the interglacial samples, so that I could really go after the extremes in the CO2 reconstructions. So the red dots over here indicate the interglacial extremes, the blue dots indicate the glacial extremes, black dots indicate transitional samples that I measured for boron isotopes. Now, these alkalinity estimates over here, this blue one, assumes that alkalinity did not change in the past. So all I did is I assumed that when salinity changes by 3%, alkalinity would also change by 3%. So that is also the small wiggles that you see here as a function of sea level or salinity change. But there's no indication that alkalinity was really constant, and there probably were changes. And those changes were estimated by David Archer for a paper that was published by Clark et al. In 2006, where he takes into account the changes in weathering rates, productivity of calcium carbonate production in the surface ocean, and calcium carbonate preservation in the deep ocean. And these two estimates over here are based on his model calculations, on David Archer's model calculations, where the red one indicates that the Canadian shield makes up about 4% of the global weathering rates, and the green one indicates that the Canadian shield makes up about 8% of the global weathering rates. And you can see that between these estimates, there are very large differences in alkalinity of over 200 micromoles per kilogram. Now, in the lower panel, you see again, these are the APICA data over here, and all these dots indicate the different scenarios that are used for the alkalinity estimates. And you can see that there's really not much of a difference between them. I can change alkalinity by 200 micromoles, and my PCO2 estimate varies by no more than 30 ppm or 30 microatmospheres. So that is a pretty good indication that I can use this alkalinity over here, and the one that matches the ice core data best is this 4% weathering assumption over here. So that's the one that I adopted for the final, or for the best estimate of carbon dioxide over this time period over here. And so what you can see over here, again, on the top we have the benthic oxygen 18 stack, and at the bottom the APICA data is the solid line over here, and the boron isotope data as the red dots over here. These dashed lines over here indicate the averages of only the interglacial samples on the upper estimate, only the glacial samples on the lower estimate, and the averages of those samples. And they agree, first of all, what I would like you to take away is that, first of all, there's a very good correlation between the boron isotope estimates and the ice core data. So overall, it looks like we can really reconstruct atmospheric CO2 from ice cores, although, of course, nothing beats the ice cores. They're much, much better than the marine estimates, but there's a very good correlation there. The next that I would like you to see is that the interglacial CO2 over this past 2.1 million years really hasn't changed very much. So this is a very good indication that there was no long-term drawdown of atmospheric CO2 over this time period. Whatever was sequestered during the glacial ocean came out again during the next interglacial. So there was no long-term drawdown of CO2. But there was a change in the glacial carbon dioxide concentration. So the glacials prior to 1 million years ago actually saw somewhat higher carbon dioxide concentrations than the glacials of the late Pleistocene. And that goes very well together with the oxygen isotopic composition of the benthic foraminifers, which for the interglacial times, for the past 2 million years, really didn't show much of a variation there. The glacial oxygen isotopes didn't show much of a variation until about 800,000 years ago, and then they slowly started to decrease. And so that is a really good indication that the oxygen isotopes in the benthic foraminifers are an indication of climate in whichever way. We cannot really tell whether it's warmer deep sea temperatures or whether it's smaller land ice extent. But during that time, the carbon dioxide concentration was relatively higher. So that is still a very good indication that climate and carbon dioxide were very intimately linked. As long as the carbon dioxide concentration is higher, the climate conditions are also somewhat warmer. So with that, I want to move on to the Pliocene, to the newest data. So we haven't seen the high concentration that we observe today in the atmosphere of carbon dioxide. And so we're still trying to find this last time in climate when CO2 was as high as today, and we would like to study the climate at that time. And there was a really nice study by Dan Lund and co-authors last year who tried to model the different forcings, the different ideas that have been put forward to explain why the Northern Hemisphere started glaciating 2.7 million years ago. And there are various different ideas: the closure of the Panama Seaway, the termination of a permanent El Niño event, and the tectonic uplift of the Rocky Mountains and the Himalayas. And all of these processes themselves, they all have some important impact on the moisture transport to the Northern Hemisphere and also the temperature there. All of them by themselves cannot create large ice sheets, and even if they all come together, they do not produce a large ice sheet. They only produce a large ice sheet when there was a large decrease in carbon dioxide from about 400 ppm to 280 ppm. So they suggested in their model that probably the Pliocene was the time when carbon dioxide was somewhat higher. So now I'm going to switch over to the other sediment core. So over here you see the data from the eastern equatorial Atlantic. Again, boron isotopes in planktic foraminifers. You see the change in the glacial values over here. So these are the eastern equatorial data. Those are the data from ODP 999A in the Caribbean Sea. And what you can already see, this is again relative to the benthic oxygen 18 stack. What you can already see is that there, particularly for this time between 2 and 4.7 million years, there was a long-term decrease in the boron isotopes. So if boron isotopes, increase in boron isotopes. So if boron isotopes are lower, that means that the pH was lower and the carbon dioxide concentration was probably higher. There's a very good correlation, again, between these data and the oxygen 18 stack. So we do not actually see the high values, the higher glacial values, until 2.7 million years. Before that time, we do not really see any of those high data. So there seems to be some sort of a step function there, but for the interglacials, we don't have the resolution to say whether there was a real step function there. But overall, this already convinced me that there's something going on that is going to be indicating higher carbon dioxide concentrations in the Pliocene. So in order to convert these into PCO2 estimate, we had to do the same thing. We had to get sea surface temperatures, salinity, which was a function of ice volume. But now we're running into real problems, because at this time we can no longer be sure that the boron isotopic composition of seawater was the same as the boron isotopic composition is today. So the residence time of boron is actually on the order of 16 to 20 million years, but for the isotopes we can really only be sure that the isotopic composition was constant for about 2 to 3 million years. So we have to assume several different things. Another thing, in addition to the boron isotopes, is that the magnesium-calcium ratio of seawater was not constant. So that gives us trouble to reconstruct sea surface temperatures from magnesium-calcium ratios. So what we're doing over here is this blue line, this solid blue line over here, indicates the carbon dioxide or the pH as a function of constant boron isotopic composition of seawater and constant magnesium-calcium ratio of seawater. The dashed line down here assumes only that the boron isotopic composition of seawater changed, but magnesium-calcium was constant. The solid line over here assumes that only the magnesium-calcium ratio was changing, but boron isotopic composition of seawater was constant. And this dashed line over here assumes changing boron isotopic composition of seawater and magnesium-calcium. And you can already see there are pretty large differences between them. Now we need a second parameter, the carbon system, and the way how we approached that is we used carbonate ion concentrations as a function of the carbon compensation depth in the deep ocean. This was work done by Richard Zeeby for us. And so he used the CCD depth in addition to changes in magnesium-calcium ratio of seawater, which is a function of the solubility and precipitation of calcium carbonate in the ocean. And so he modeled those data for the past 2 4.2 to 4.7 million years ago. These are the data over here, so you can see how the carbonate ion concentration 4 million years ago was lower than it was 2 million years ago. Over here you see the different pH estimates again. And then at the bottom we used now these pH estimates with those carbonate ion concentrations to calculate carbon dioxide concentrations. And the really interesting part is over here, these two lines now come together. So this is the line where we neither assume boron isotopic composition of seawater or magnesium calcium changed. That's the one, and the other one is where both parameters changed. So the relative effects of the magnesium calcium ratio on the temperature and the isotopic composition pretty much cancel out. So we get similar estimates for both of them. And I think this is probably the best estimate that we have for that time. And what you can see is this is the pre-industrial carbon dioxide concentration that during the Pliocene this level was exceeded by quite a bit. So we're going to values that are somewhat similar to what we see today. If only the magnesium calcium changed, then the values would be even higher than that. But there is some indication that these values have changed. And with that, I'm coming to the last slide. So to summarize all this, the carbon dioxide concentration has not been as high as today for at least 2.1 million years. That's what we take out of the mid-Pleistocene study. The MPT glacials saw relatively higher carbon dioxide, but the interglacial carbon dioxide was similar, and that argues against a long-term drawdown of atmospheric CO2. But there's a very good correlation with the benthic oxygen 18 stack, and that indicates that there is a real intimate coupling between PCO2 and climate. And the last time that PCO2 was as high as today was likely during the Pleistocene, but in order to get real better estimates of that, we need to have a better understanding of the isotopic composition of seawater. And with that, I'd like to close here and thank you for your attention.